Hi everyone, this is Miss P, and this is comparing fractions part 2 using a little bit more complicated fractions. In the last video, we used fractions where the denominator was the same in each fraction, or where the numerator was the same in each of the two fractions, or where the denominators could be compared in that one of the denominators was a factor of the other denominator. In the case of the fractions we're going to look at today, the denominators are going to be different. They're not going to be a product of one another, and they're not going to share a factor. That means we're going to have to approach comparing these fractions in a little bit of a different way. We're going to start by comparing these two fractions, 3/5 and 5/7. As we look at these fractions, we're going to notice that the two denominators, 5 and 7, are not common, and they also don't share a factor. In this case, it's pretty obvious, but with bigger numbers, what I like to do is I like to take the smaller of the two denominators and I like to skip count to see if the second denominator falls within its multiples. So in this case, I would say 5, 10, 15. Okay, well, I know 7 is not going to fall within the multiples of 5, so 5 is not a product of 7. So I can't use the strategy that we used yesterday. So instead, in order to accurately compare these two fractions, we still have to find equivalent fractions for each of them that share a denominator. So we're going to have to somehow convert both of these fractions into equivalents that share the same denominator. In the case of different denominators like these, where they don't share a factor, you can simply multiply the two denominators by each other to find a common denominator. In this case, 5 times 7 equals 35. And if we convert both 3/5 and 5/7 into equivalent fractions that are represented using 35ths, we will be able to determine which is the greater fraction. We can start by converting 3/5 into a fraction represented in 35ths. So as you can see here, we have 3/5 and we'd like to convert it to 35ths. So what we're going to do is determine what we do with the 5 in order to make it into 35. And in this case, we can go right back up to the equation that we created to determine which denominator we were going to use. And we can determine, okay, 5 times 7 equals 35. Because 5 times 7 equals 35, in order to find the equivalent fraction, we have to do the same thing, perform the same operation with the numerator as we did with the denominator. So we will multiply 3 times 7. And we know that 3 times 7 equals 21. And so the equivalent fraction of 3/5 is going to be 21/35. Excellent. Now that we've determined the equivalent fraction for 3/5 to be 21/35, we next have to find the equivalent fraction for 5/7. So we know that in order to reach the denominator of 35ths, we multiplied the 7 in the original denominator times 5 from our equation up here. Whatever we do to the denominator, we have to also do to the numerator. So we have to multiply the numerator also times 5. So 5 times 5 is 25. Now we can say that the equivalent fraction for 5/7 using that common denominator of 35 is 25/35. And since we have common denominators in the equivalent fractions, we can look to the numerators and determine that 21/35 is less than 25/35. Since these fractions are equivalent to our original problem here, we can apply the same logic and determine that 3/5 is less than 5/7. Now this works for small numbers, smaller denominators like 5 and 7, but it also works for bigger numbers and larger denominators. We can apply this rule to really any two fractions that we're comparing. So let's use this strategy with a slightly more complicated problem of comparing fractions. In this example, we're asked to compare 15 43rds to 10 29ths. Now, as you might notice, the denominators in these two fractions are much bigger than the denominators we've been using so far. I purposely chose prime numbers to use as the denominators in this example so that we could immediately determine that there is no common factor that we could use with these two denominators. We're going to have to use the strategy where we multiply the denominators by each other to get a larger number for our denominator to find equivalent fractions in order to compare. So in this example, because 43 and 29 are both prime numbers, we're simply going to multiply 43 times 29 in order to get a number that will work as our common denominator. At this point, this number is large enough that you probably will have to write out the problem to solve it. So let's go ahead and practice 43 times 29. And we can multiply here the ones column first. 9 times 3 equals 27. Regroup that 2. Multiplying the 9 ones by the 4 tens here. 9 times 4 is 36, plus the 2 is 38. Already used that. Starting with my 2 tens, multiply it by my 3 ones. That gives me 6 tens. I can fill in my ones place there with a 0 as a placeholder. Then multiplying my 2 tens times my 4 tens, which gives me 8 in the hundredths place. Okay, adding up my two partial products here. 7 plus 0 is 7. 8 plus 6 is 14. Regroup that 1. 1 plus 3 is 4. 4 plus 8 is 12. So we have a product of 1,247. Now, 1,247 is really large for a denominator compared to what we've been working with so far, but this is going to be a way that we can precisely, in finding equivalent fractions, determine which of the two fractions we started with, 15 43rds and 10 29ths, is greater and which is less. Okay, so our next step is to take the first fraction, 15 43rds, and to find the fraction that's equivalent to it that has the denominator of 1,247. So we have to determine what do we multiply 43 by in order to get 1,247. Well, we know because we did the work up here. We've got our work shown here. You can just remember that it is 29, okay? So 43 times 29 equals 1,247. And so I've got to do the same thing with the numerator as I did with the denominator. And again, this might be, these numbers are bigger. You might want to write out your work here. 15 times 29. We can start with my 9 ones times 5 ones is 45. Regroup that 4. 9 ones times 110 is 9, plus 4 is 13 tens. We've already used that up, so starting with our 2 tens times 5 ones, that gives us 10 tens. So we'll regroup our 1 here, add a placeholder 0. 2 times 1 is 2, plus 1 more is 3. Add up our partial products here. Gives us 435. So the fraction that we have created that is equivalent to 15 43rds is 435 1,247ths. Next, we have to take the second fraction that we're comparing here, which is 10/29ths, and we have to convert that fraction to the equivalent fraction using 1,247 for the denominator. So we have to determine how do we get the 29 to become 1,247. And the answer, if we look up at our equation up here, is we multiply it by 43, right? Our factors in our multiplication problem can be switched around to get the same answer. So 43 times 29 is the same as saying 29 times 43 as far as what answer we're looking for. We then do the same thing to the numerator as we've done to the denominator. We multiply it by 43 as well. I could write this out, but I also find this a little bit easier to multiply just by looking. 43 times 10 is going to be 43 tens, so it's going to be 430, 43 tens place. Now I've determined that the equivalent fraction of 10/29ths is 430 1,247ths. Now that I have found the equivalent fractions with a common denominator for both of the fractions that were given to me, after identifying that the denominators in these equivalent fractions are the same, I can look to the numerator to determine which fraction is greater. And in looking at this, I can see that 435 1,247ths is greater than 430 1,247ths. Once I've identified that, I can apply that answer to our original problem here. And since I know the equivalency of each fraction, I can confidently say that 15/43 is greater than 10/29ths. This is a strategy that can be applied to really any fractions that are being compared, but is specifically useful when you are comparing fractions that do not share a common factor. That's often found when one of your denominators is a prime number, or when the two denominators simply are different enough that they do not share a common factor. This strategy can be applied for any size numbers and is helpful anytime that you are asked to compare fractions.